Hey, congratulations on reaching the second last chapter of the physics syllabus. So this chapter is called Electromagnetism. So before you can understand this chapter, you will definitely need to read up on magnetism. What is new in this chapter is this word electro. So previously when you learn about magnetism, you learn that magnetism arises when the domain in material is being aligned, right? Then it will produce this magnetic effect. But most of the example given is fixed. For example, what I mean by fixed, it means that if you have a permanent magnet, the magnetic effect of this permanent magnet is permanent, right? You cannot switch it off. But when we come into this chapter called electromagnetism, as the name suggests, right, we are going to use electricity to produce a magnetic effect. So in this case, it means that you will now have the power to turn on and turn off the magnetic effect at will. And this gives you many advantages because when you have a material that can produce magnetic effect, it can interact with another material that has a magnetic effect, and you can produce a force that is either repulsive or attractive in nature. And because magnetic forces are non-contact, you can basically manipulate an object at will because now you can produce this magnetic effect at will. Okay, so before we move deeper into the chapter, this chapter doesn't have any calculation question. It is mostly descriptive. And the second thing unique about this chapter is that it is now no longer one-dimensional, it is three-dimensional. So in three-dimensional space, we are still writing on a piece of paper, right? So we need to learn some technique on how to describe three-dimensional space on a two-dimensional paper. So I will give you a few scenario and to illustrate that. So for example, now you are reading this worksheet on the table, right? So that is you, and then that is the paper. Meaning that this paper, right, is a plane. So when we describe this paper, right, this is the convention that we used to do. We will say that, this is the top of the paper, and then below your desk is the bottom of the paper, right? Like the ceiling is the top. But now because we have to describe three-dimensional space, right, this top, bottom, up, down, left, right, has to be clearly defined. So now what is the top? The top is actually referring to the top edge of the paper, and this is now the bottom. So for example, if you want to describe something that goes like that, it is not called going up anymore. It's going to the top. This is going to the bottom, and then this is going to the left, and of course this is going to the right. Now, having this sign convention allows you to describe a two-dimensional space because now you are talking about the directions that is available to you on this piece of paper. What if you need to describe something that goes like that? And what if you need to describe something that goes like this? So this is what we call out of the paper. Okay, and this is what we call into the paper. So in another word, right, this out of the paper, it is a direction that is going to the ceiling. And this into the paper, right, is basically a direction that goes to your floor. Okay, so how can we represent this out of the paper and into the paper direction on a piece of paper that is two-dimensional? So just to highlight, this out of the paper, right, in exam, if you say that it will go up, we won't accept that. Or if you say it will go to the top, we will think that you are referring to this top. Sorry, wrong pen. If you say in your descriptive description, right, you are going to the top, we will think that you are referring to this. So the correct terminology now is, if you want to describe something that goes to the ceiling, it's called out of the paper. Now it is quite hard to draw this out of the paper unless, like me, you go and define a plane like that first. But in exam, you won't have time to do that. And for some of you who can't really draw, it's difficult. So physics, right, define a system to do this. How they do it? You imagine you are looking from the top of the paper, and if there is an arrow coming out from the paper going to the ceiling, for example, imagine that there is a 3D arrow, okay, that is now going out of the paper and into the ceiling, and your eyes is right there. What would you see? You will see that there will be this part, the circumference of the cone, and then after that you will see a dot, this dot coming towards you. So in physics, right, when we want to define an arrow or a vector that is coming out of the paper, we would draw a circle and a dot. Means that this thing is going out of the paper. And what if I want to describe something that goes into the paper, that means towards the floor? You imagine your eyes is here. You will be seeing the back side of the arrow, meaning that you will see this, and then the other two feather, right? So in your eyes, you will see like that, right? If I draw it properly, if you don't get what I'm saying, if I draw this part properly, it will look like this, right? This is the rod of the arrow. Then after that, you got the feather here, right? Then after that, you got another feather here. Then here is another feather. Then here is another feather, right? So in total, there are 1 feather, 2 feather, 3 feather, 4 feather. And if you look at the back, it will appear as if it is a cross. So on a piece of paper, if you see a cross, it means that the question is trying to tell you that now there's a vector that is going into the paper and down towards the floor. So for example, if now I want to represent this 3-dimensional space, what is 3-dimensional? Left to right is 1 dimension, top to bottom is 1 dimension, out of the paper and into the paper is 1 dimension. So that is 3-dimensional space. If I want to draw it on a piece of paper, it would be top to bottom, left to right, and then if I want to define that there's a vector coming out of the paper, I will do this. And if I want to say that down here there's a vector that goes into the paper, I will do this. Okay, sometimes you will see that there's an arrow there's a circle as well, because if you look from the bottom, you will see this cone over here. Okay, if you can't see this cone, the green color one. Okay, so this is the first thing that you should know in this chapter. How do we define the 3D space in a 2-dimensional object? So for example, if I want to say something that goes, how do I say this? This is not go up, this is go to the top, right? Top edge of the paper, right? If you want to go to the right, very straightforward, go to the right, right? This one is going into the square, right? Into the cube. So going into the paper, what do you use? I give you 3 seconds to think. Into, that means going towards the floor. So you will see the back side of the arrow, right? You will see this, right? Then this one going out of the paper, so meaning that your eyes is here, going out of the paper, right? So you will see that the arrow head is coming towards you, right? For those of you who can't see that, this is what I mean. This going into the paper, right? I'm referring to this going into the paper, right? So you will see the back side of the arrow, so it's a cross. Can? Now that you know what does this dot and cross mean, right? Then let's go to the main part of our lesson. So previously I said, right, if you have a magnetic object and that all the domains are aligned, you will realize that it will produce a magnetic effect, right? So I repeat, what are some keywords that I say? I say domain, I use the word align, and then I say produce magnetic effect. Notice I didn't say it turn into a magnet, I say it produce a magnetic effect. In order for it to turn into a magnet, right, I have to lock the domain in places, but I don't know, right? If it is a hard magnetic material, then I can lock it, right? Because it will stay there for a long time. So what is an example of a hard magnetic material? I'm doing a recall now. 3, 2, 1, steel. Okay, if you have steel, then once you align the domain, it will lock into place. You will have a magnet. But if you are aligning the domain on a soft magnetic material, which is 3, 2, 1, iron, then you won't have a permanent magnet, because after you align the thing, once you leave the whatever influencer you have on the material, the domain will just go back to its messy state. Then it will lose its magnetic effect. So get used to using this term, magnetic effect, align, domain, produce. You need to get used to the terminology. If not, you'll find that when you explain questions, it will be very difficult. Now, this is the start of magnetism, right? Alignment of domain produces magnetic effect, right? Then, by the different nature of the material, whether it's hard magnetic material or soft magnetic material, we will know that whether this magnetic effect is going to stay or not. Now we bring you out of the magnetism chapter and we show you something similar. Now, in the previous chapter, we learned that if I have a positive terminal and I have a negative terminal, it will produce a potential difference across this wire, right? And when this happens, a current will flow, correct or not? And of course, we are using conventional current because that is our norm now, right? So what happens is that in a conventional current, you will have a net flow of electron, correct or not? So when the electrons are all flowing in one direction, it will become very similar as if that the domain has aligned. And because of that, we discover that this current, right, will also produce a magnetic effect. Meaning that they realize if you turn on the current, there will be magnetic effect. You turn off the current, the magnetic effect will be gone, right? There's nothing to lock it in place. So we realize that, hey, I can turn on magnetic effect on wheel. So this is why we have this chapter. We want to study this phenomenon. Now, what is strange about this is that in your previous chapter, you learned that the magnetic field will go like that, draw with a ruler. Then after that, it will be like a spider like that, right? Similar to your electric field. Now, when you pass a current through a conductor, the resulting magnetic field will look like a circle and it will form rings around this conductor, right? So for example, if now I imagine that there is a current going from the floor to the ceiling, right? And I want to represent it on a piece of paper, this current that I'm drawing, how would I represent it? Take note of what you have learned. I have a current that goes from the floor to the ceiling. Okay, floor to the ceiling. How should I represent this current on my piece of paper? Should I represent it with a dot or a cross? A current going from the floor to the ceiling. Think, I give you 3 seconds. Okay, I hope you have made a choice. So if I'm going from the floor to the ceiling, and of course I am reading the paper from the top, right? I will be seeing the arrow popping out from the paper and into my eyes. So if I want to represent this current I1, I would have drawn this I1. And as I know, the magnetic field that will be produced by this current or the magnetic effect when it is produced, it will also produce a magnetic field, right? So if now I want to sketch this magnetic field on my paper, the magnetic field will go in circular in nature. Maybe I use red like that. And of course, the further it is from the wire, the weaker the field, right? So as you can see, my circle, the gap between the circle is getting bigger and bigger. Now what if I want to represent a current that goes into the paper? and then goes to the floor. Let's call this I2. How would I represent it? Give you 3 seconds or so. Right? You are reading from the top. You have a current going into the paper. Yes, I hope you have made the right choice. You will see a cross. Right? And then if I want to represent its magnetic field, it will be another circular nature. Right? Correct? So, in this first page, what we have learned is that, okay, this is how we define 3D space. This is the sign convention, how to represent 3D space on a piece of paper. Then I go through with you how from magnetism we translate to electromagnetism. The new keyword that we are learning are domain, align, magnetic effect, hard, soft material, whether the domain alignment will be locked. In electromagnetism, there's PD across the conductor. The PD produce a current, which is very similar to the alignment of domain. It will then produce a magnetic effect, and because there's a magnetic effect, I can sketch a magnetic field. And then I combine what we have learned, this sign convention, and I show you how to represent a current on a piece of paper and its accompanying magnetic field. So to the end, for this part of the video, we say that what is meant by magnetic effect of the current, we say that, oh, when a current flows through a conductor, the domain of the conductor will be aligned, right? Similar to what you learn in magnetism, when the domain aligned, hence a magnetic field will be produced, and because this magnetic field is produced, we say that the current will produce a magnetic field. And because this magnetic field is non-permanent, we use this word induce. It means that it is a temporal, it is affecting it temporarily, right? Induce means it is not permanent. When the current goes away, the magnetic field also goes away. Just like your class lah, if there's a teacher, wow, all the students, wow, very nice, right? When I'm around, you all behave at the best. Then when I turn my back and go out, all become monkey already. So this is called induction of Mr. Choi, right? I induce the class to behave themselves, right? So this is the first part of the video, and I hope you can digest it. If not, go for a break and come back for part 2 of the video.